Welcome to Hartman Math. Today we're going to talk about right triangle trigonometry as well as trig functions of any angle. Prior to that, we have a warm-up reviewing some of the stuff that we've been doing in our trigonometry chapter. Go ahead and pause the video here, where we're looking to convert to degrees, convert to radians, given part of a circle there, the length of the arc that is intercepted. Number 4, evaluate cosecant of pi. And number 5, the tangent of 450 degrees. All right, number 1, if we multiply by 180 degrees over pi, pi's cancel, and we're going to get negative 75 degrees. Number 2, multiply by pi over 180 degrees. Degrees cancel. Divide 36 and 180 by 36. And we're left with 5 in the denominator, so pi over 5 as our angle in radians. Number 3, arc length is radius times theta. Theta does need to be in radians, so we do need to convert from 150 degrees into radians. So that would be 5 pi over 6 multiplied by 3 is 5 pi over 2 meters. And then for number 4, we're going to need to know where those are in terms of the coordinates and where is the angle. So pi is going to be straight left, negative 1 comma 0. Cosecant of pi would be the reciprocal of the y-coordinate. And since 0 does not have a reciprocal, that would be undefined. And then for the tangent of 450 degrees, 90 degrees, 180 degrees, 270 degrees, 360 degrees. Ooh, there, puts us right there. Another quadrant angle, 0, 1. The tangent would be the y-coordinate divided by the x-coordinate. And 1 divided by 0. Since you can't divide by 0, that's also undefined. Lesson 4.3 is right triangle trigonometry. So we're going to be dealing with physical triangles. So not necessarily the trig angles that we were looking at in 4.1 and 4.2, which had an initial side on the positive side of the x-axis, and then we're talking about rotating. We're talking about physical angles, so really more in a geometry sense. And our trig functions, our 6 trig functions, are defined as sine of theta is equal to opposite divided by hypotenuse. Cosine of theta is adjacent divided by hypotenuse. Tangent of theta is opposite divided by adjacent. When you initially learned this, possibly back in Math 2, you might have heard the phrase SOHCAHTOA. SOHCAHTOA. That sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. And that's for our 3 primary functions. And that comes from SOHCAHTOA, is the Native American word for trigonometry. No, that's not true. That's a lie. There is no Native American language for all of them. They have separate languages, in case you hadn't known. And then the cosecant, those are just the reciprocal functions. So we just flip those. And so hypotenuse divided by opposite, and so on. So example number 1, use the given information here to find the values of the 6 trigonometric functions of theta. Well, if we do need to know all 6, we're going to need to know all 3 sides of the triangle. So that's where we have to start. It is a right triangle. It's designated by the box indicating the right angle. And we do have a missing side. So think about it for a moment. How would you find the missing side of our right triangle? And if you were thinking Pythagorean theorem, that would be correct. So because of a squared plus b squared equals c squared, and we are trying to find the side that's opposite of the right angle, trying to find the hypotenuse, which in this case would be the c. We're talking about 5 squared plus 12 squared equals c squared. We would come up with 13. Now, some of the common right triangles you might also know and just kind of have some of those memorized, and they're called Pythagorean triples. Anytime you have three values that are whole numbers that fit for the sides in a right triangle, those are called Pythagorean triples. This is probably the second most common Pythagorean triple, the 5, 12, 13. The most common being the 3, 4, 5. So if the two legs are 3 and 4, then the hypotenuse is 5. And another one that's very common is the 8, 15, 17. I bet we see that at some point coming up. All right, so for the sine of theta, where our angle theta is here, sine is opposite divided by hypotenuse. So opposite, you would go across from the theta. There's our opposite of 12. 13 is always going to be our hypotenuse. And then for cosecant, we could just flip that, say it's 13 over 12. Cosine is adjacent. Adjacent is the leg, not the hypotenuse, but the leg that touches the angle. So that would be the 5. 5 over 13. And then reciprocal to get secant, 13 over 5. And then tangent would be opposite divided by adjacent, 12 over 5. Cotangent, the reciprocal, 5 over 12. Now, some fundamental identities that you would need to know. Some of these we kind of have an idea about. The sine of theta is 1 over cosecant theta, or therefore the reciprocal. And that works in reverse as well. So cosecant of theta is 1 divided by sine theta. That could be useful for a calculator problem. Let's say it said to approximate the cosecant of 22 degrees. You can just type in 1 divided by sine of 22 degrees, as you probably don't have a cosecant button on your calculator. So those are our reciprocal identities. Then we have the quotient identities. Because tangent is y over x, and in the unit circle y is sine, and in the unit circle x is cosine, we could also say the tangent of theta is the sine of theta divided by cosine of theta. And then cotangent being the reciprocal, if we just flip that, we get the reciprocal functions as well. Pythagorean identities. Sine squared theta plus cosine squared theta equals 1. If we were to have a look at that back in the unit circle, where this is the point x comma y, we have already said that the x-coordinate is just cosine of theta. So that would be cosine of theta would be the x, and the y would be the sine of theta. So according to that, and we know it's the unit circle that the radius is 1, a squared plus b squared equals c squared, sine squared plus cosine squared theta is equal to 1. Kind of notice the notation here, which is a little bit different. Sine squared theta does mean sine of theta in parentheses squared. It's just a common notation that is used. If you wrote sine of theta squared without parentheses, it would mean the sine of square the angle theta, and that's not quite the same thing. So this means sine of theta times sine of theta. With this one identity, you can generate all the other Pythagorean identities. And in truth, there are really 9 of them in total. Because we could take this one and then algebraically manipulate. Let's say I subtracted sine squared from both sides. One identity I could get is cosine squared theta equals 1 minus sine squared theta. That will be very useful later. And then if I just subtract cosine squared from both sides, I'd get sine squared theta is equal to 1 minus cosine squared theta. If I divide everything by cosine squared theta all along, I'm going to get this one. And then we can manipulate that and say, oh, okay, if I minus 1 both sides, I get tan squared theta is equal to secant squared theta minus 1. Or 1 is equal to secant squared theta minus tangent squared theta. We get the last one by taking our initial identity here and just dividing everything by sine squared theta. If I divide that by sine squared theta, if I divide that by sine squared theta, I get cotangent squared theta. And dividing this by sine squared theta, we would get cosecant squared theta. So there are 9 Pythagorean identities. These are kind of the primary ones. But it all comes from, if you don't want to memorize all 9, and I don't, it all come from algebraically manipulating the first one. Okay. Also, cofunction identities. These are all in radians. We could do them in degrees. We replace pi over 2 with 90 degrees. But these are all in radians. So the idea on cofunctions kind of would be the phrase that pays here, is that cofunctions, and your cofunctions, the ones are related by this identity, sine and cosine, tangent and cotangent, secant and cosecant. So not necessarily the reciprocal ones, but these are the cofunctions. Cofunctions of, and here's this part, the pi over 2 minus x, we recognize that from prior, back in 4.1, as being complements. Cofunctions of complements, x and pi over 2 minus x, those are complements. If we were talking about in degrees, it'd be like 20 degrees, 70 degrees, are equal. Cofunctions of complements are equal. So in terms of degrees, we would be saying the sine of 70 degrees will always equal the cosine of 20 degrees. Because sine and cosine are cofunctions, the angles are complements. So these are the cofunction identities. All right, example number 5, applying trigonometric identities, the ones that we were just looking about, that often can be found in the book itself, either in this part of the 4.3 or possibly at the front or back covers oftentimes as well. We are given an angle and we want to find cosine of theta being 8 over 17. It is an acute angle, so we're talking about a physical angle. So find, part A, find sine of theta. Well, we need an identity that relates sine of theta and cosine of theta, the theta being arbitrary. So if we go back and look for a second, is there an identity that relates sine and cosine? Well, there are a few. There's this one. The problem with this one is it also uses tangent. We have no knowledge of tangent, so that's probably not a good one to go with. What else do we have? We have these. The problem with the cofunction is the angles aren't the same. It would be not the same angle, so different angles. And our problem was both theta, so same angle. So this isn't going to work. But this one might. This is an identity that uses sine and cosine. So we could use that one to say, in the algebraic manipulation of that primary one, that sine squared theta is equal to 1 minus cosine squared theta. And you could start with the other one. It just takes more algebraic work to get there. But we would use this one because we are trying to find sine, and this means we're really close. Okay. Just a hint also. It does not work when it's sine theta equals 1 minus cosine theta. You cannot square root all of the parts. That would be highly illegal in terms of operations. So it's only true for the functions that have been squared. And that's true of the Pythagorean ones. All right? So now we're ready to replace. We know that cosine of theta is 8 over 17. So we're going to put that here. And cosine squared theta means take cosine theta and square it. So we're talking about squaring the 8 over 17. And then we're going to need to square that, numerator and denominator. And then we're going to need to get a common denominator to do the subtraction. And the common denominator is, I think, the 17 squared, which is 289. So if we now subtract those, sine squared theta is equal to 225 over 289. Square root both sides. Because we're talking about an acute angle, we really only care about positive value here. So sine of theta is 15 over 17. Part B, find tangent. So we need, now we've got cosine, we've also got sine. We've got both of those. Can we find how tangent is related to cosine and or sine? Again, let's go back and look at our identities. Where do we have tangent? Not useful. That one might be useful. This one's good if we know sine and cosine. And we do now that we've done part A. So let's use that identity, the quotient identity. Tangent of theta is sine of theta divided by cosine of theta. We've got our sine of theta here. We've got our cosine of theta there. So we're talking about 15 17ths divided by 8 17ths. We do have a complex fraction, which is a fraction divided by another fraction, or just numerator, denominator, having a fraction somewhere in there. But this one's pretty easy. I mean, we could, instead of dividing by 8 over 17, multiply by the reciprocal. That's one strategy. But noticing that we saw this also in the unit circle stuff, is if we're dividing and they're complex fractions and the denominators are the same, that just kind of goes away. So we're just left with 15 over 8, that being our answer for the tangent of theta. Example 6, another acute angle. We've got theta. Again, we're going to work on using the trigonometric identities. We've got cosecant of theta being 5 over 2. Find sine of theta. Well, they're pretty closely related. They are reciprocals. So that part A should be an easy one. They're reciprocals. All we got to do is take this one and flip it, take the reciprocal. So sine of theta, we're going to use the reciprocal identity, and as being 2/5. Now cotangent. That one's going to be a little bit more challenging. Okay, so if we're don't want to have the identities memorized, I'm kind of thinking that cotangent is related to tangent. But we only have this and sine. We don't have anything about cosine or anything like that. So we might need to do some identity work. So again, if you got to memorize that, it's great. You'll know which Pythagorean identity is going to relate cotangent to one of these. But if not, we're just going to go back to sine squared theta plus cosine squared theta is equal to 1. From this, how would we get cotangent theta, or more exact, cotangent squared theta? Well, if we took cosine squared theta and we divided by sine squared theta, that's the quotient identity, we're going to get cotangent squared. But I got to do it everywhere. So we're doing that, we get 1 plus cotangent squared theta is equal to cosecant squared theta. We want to get the 1 for cotangent. If I just go minus 1 on both sides, that's the one that we want. Cotangent squared is cosecant squared theta minus 1. All right, cosecant squared is right there. So cosecant theta is 5/2. We're going to have to square that. So 25 over 4 minus 1, or minus 4/4. 21/4. Square root both sides. Again, it's acute, so we're going to only worry about the positive answer. So cotangent theta is positive square root of 21 over 2. There is our cotangent. Example number 8, solving a right triangle. A biologist wants to know the width of a river in order to properly set up instruments for studying pollutants in the water. From point A, the biologist walks downstream 70 feet and then sights straight across to point C. from this sighting is determined that the angle from the original position to that point over there is 54 degrees. How wide is the river? Okay. So the 54 degrees is the angle that we care about. We're looking to find the opposite. So opposite's going to be important. And we know the adjacent. So we're thinking about the trig function that includes opposite and adjacent. We don't care about the hypotenuse. We're not trying to find the hypotenuse. We don't know the hypotenuse. We don't want to use hypotenuse. So that means we're using tangent. Tangent's the one. Tangent of our angle 54 degrees is going to be opposite divided by adjacent. Solve for W. So we have to undo the division, multiply both sides by 70. So W is equal to 70 times the tangent of 54. Now you're ready to type it into the calculator. Make sure you're in degree mode, because if you're in radian mode, you're going to get a different and wrong answer. Make sure you're in degree mode, type it in, round it off, provide units. We get that that's pretty close to 96 feet across. Section 4.4, trigonometric functions of any angles. Kind of connects the right triangle trigonometry back to the unit circle. It says we got a point that's maybe not necessarily on the unit circle, just some distance away. If we know the coordinates, sine of theta would be y divided by r. Now if we were on the unit circle, the radius would be 1. Y divided by 1 is just y. That's why in the unit circle, sine of theta was just y. But in general, sine of theta is y divided by r, where r is the distance from the origin to that point. And you can find r by doing a little Pythagorean theorem or distance formula. It's the square root of the coordinates squared added together. Cosine is theta is x divided by r. Tangent of theta, because it's a ratio, is still just y divided by x, as long as x is non-zero. Reciprocal here. Flip that one to get secant. Flip this one to get, flip this one to get secant, and that one to get cosecant. Kind of threw me off with the order that they were placed there. So if we've got a point that is on the terminal side of an angle, can we find sine, cosine, tangent? And if we could find those three, we could definitely find the other three as well if we needed to. So let's think about this in terms of a sketch. Which quadrant would this be? Let's kind of sketch it there in the correct quadrant. And then if we're drawing a trig triangle to associate with that point that has gone left 8 and down 15, one side of your trig triangle is always going to be on the x-axis, never on the y-axis. Always on the x-axis. So our angle theta is represented by that rotation right there. All right, so the other thing that we need to know is the r. So we'll do r is equal to the square root of x squared plus y squared. If we do those calculations, told you this was going to come up, we're going to get 17, because that's a Pythagorean triple. 8, 15, 17. Mark that in there as 17. Now as far as sine of theta, in any angle, always going to be the y-coordinate divided by r. So negative 15 divided by 17. And then cosine of theta is the x-coordinate divided by r. And tangent of theta, we could think in terms of sine of theta divided by cosine. But it's probably easiest just to go back here. Y divided by x, a negative divided by a negative, definitely going to be positive. Remember, in terms of our coordinate quadrants, all students take calculus T. Tangent's the only one that's positive in quadrant 3. Negative, negative, positive for tangent. Make sure that the sign is correct. If we needed to get cosecant, flip, and so on. Example number 2. given the tangent of an angle being -3 and some additional information, sine of theta being less than 0, find sine of theta and secant of theta. And the reason that we need the additional information is to help us determine in what quadrant is theta. So we're going to start with tangent of theta being negative. In which quadrants is tangent negative? 2 and 4. So far, we're kind of thinking, as a clue here, our quadrants either got to be 2 or 4 from the first piece. Now, between 2 and 4, where is sine of theta less than 0? Where is sine of theta negative? Only in one of those, and it's quadrant 4. So that's how we know which angle. Both pieces kind of the given information and the clue. All right, so now let's see if we can sketch in quadrant 4 a trig triangle where one of the sides is on the x-axis and it represents this situation. So remember, tangent of theta is opposite divided by adjacent. So opposite -3, adjacent +1. That fits our description for the tangent of theta being -3. Now we can do the Pythagorean theorem to find the hypotenuse. Or since these are just coordinates, we can think of it that way. 1, -3. You can also just do the square root of x squared plus y squared. And either way you do it, you do get the square root of 10. So now, what is sine of theta? Sine is, whether we want to think of it as the y coordinate divided by r, or in terms of our angle theta, opposite over hypotenuse, -3 over root 10. Just a reminder, you do not have to rationalize the denominator. And secant would be the reciprocal of cosine, therefore r divided by x, or hypotenuse divided by adjacent. Root 10 divided by 1 is root 10. All right. Reference angles. Definition of a reference angle. It's an angle in where theta is an angle in standard position. The reference angle is the acute angle, theta prime. So it's an acute angle. It's a physical angle. Okay? In degrees, it has to be between 0 and 90 degrees. In radians, therefore, it has to be between 0 and pi over 2 radians. It's formed by the terminal side of theta and the horizontal axis. So it's essentially the fastest way to get to the x-axis. So for example, if we were in quadrant 2, the fastest way to get from here to the x-axis is just to rotate here. That's the reference angle. Here's how you can find it. Pi minus the original angle, or 180 degrees minus the original angle. If we're in quadrant 3, we're going to go the other way. That's the fastest way to get to the x-axis. So it's that angle right there. So since the angle is past pi, it's the angle minus pi in radians, or the angle minus 180 degrees if we were in degrees. In quadrant 4, the fastest way to get to the x-axis is just to keep rotating that way until we hit it. So 2 pi minus theta, or 360 degrees minus theta. Notice what was not mentioned is quadrant 1, which is why, because in quadrant 1, any angle is its own reference angle. So we're talking about, hey, we're talking about 52 degrees, that's in quadrant 1. What's the reference angle? 52 degrees. Fastest way is just to go right back to 0, so it's just 52 degrees. Find the reference angle for where theta is this. Theta prime, that's our notation to designate reference angle. Theta with the apostrophe, theta prime designates the reference angle. So we could kind of take a look at sketching this, 7 pi over 9, kind of good practice if we were to kind of think about top half of the circle, we're in radians, so this is definitely pi straight across. Let's divide it into 9 equal pieces. 1, 2, 3, 4, 5, 6, 7, 8, 9. And we're going to go to 7 of those. So 1, 2, 3, 4, 5, 6, 7. That's where we're at. And if that's where we're at, we're here at 7 pi over 9. We only got to go 2 pi over 9 more to get there. So the result here, we just do pi minus 7 pi over 9 to get that. Part B, 310 degrees. We're going to have to know where that is. This one's in degrees. We'll keep it in degrees. 90 degrees. That's possible. 180 degrees. 270 degrees. We're a little bit past that. In fact, we're 40 degrees past that. Might be useful to kind of get that in there. So there's our 310 degrees. So the reference angle would just be this one here to go from there to there. So what's left over? 50 degrees. Or 360 minus the 310. 50 degrees is our reference angle. Example 6. Got some information. Theta is in quadrant 3. Good hint. And in there, sine of theta is going to be negative 5 over 13. Find sine of theta and tangent using trigonometric identities. All right, so identities means we're not really allowed to sketch this one out. We're going to have to use identities. Okay? All right, so given we have sine of theta, got a couple ways we can go. We would always also know cosecant. Find secant. That's closely related to cosine. I'm thinking maybe we go cosine and sine. Sounds like Pythagorean. So cosine squared theta is equal to 1 minus sine squared theta. One of our Pythagorean identities. Plug this in there. 1 minus parentheses negative 5/13 squared. In which case we get positive here, 25 over 169. And this becomes 169 over 169. So we get 144 over 169 for cosine squared theta. Now we're going to need to square root both sides. So to square root both sides, we've got to decide if we're going to go with the plus or minus. Is it positive or is it negative? Let's go back to our clue. Quadrant 3, talking about secant, which is related to cosine. In quadrant 3, cosine is negative. So we're going to want, when we square root both sides, we're going to want negative 12 over 13. And now to get secant, just do the reciprocal. How do we get tangent? Well, we know sine. We know cosine, quotient identity. Here divided by here, negative divided by negative. Denominators cancel, 5 over 12. That's it for today. I'll see you next time.